Iron, Fe, is a relatively dense metal with a silvery white appearance and distinctive magnetic properties. It constitutes 5% by weight of the Earth's crust, and it is the fourth most abundant element after oxygen, silicon, and aluminum. It melts at a temperature of 1538 degrees Celsius, 2800 degrees Fahrenheit. Study the production and structural forms of iron from ferrite and austenite to the alloy steel. See all videos for this article. Iron is allotropic, that is, it exists in different forms. Its crystal structure is either body-centered cubic, BCC, or face-centered cubic, FCC, depending on the temperature. In both crystallographic modifications, the basic configuration is a cube with iron atoms located at the corners. There is an extra atom in the center of each cube in the BCC modification and in the center of each face in the FCC. At room temperature, pure iron has a BCC structure referred to as alpha ferrite. This persists until the temperature is raised to 912 degrees Celsius, 1674 degrees Fahrenheit, when it transforms into an FCC arrangement known as austenite. With further heating, austenite remains until the temperature reaches 1394 degrees Celsius, 2541 degrees Fahrenheit, at which point the BCC structure reappears. This form of iron, called delta ferrite, remains until the melting point is reached. The pure metal is malleable and can be easily shaped by hammering, but apart from specialized electrical applications it is rarely used without adding other elements to improve its properties. Mostly it appears in iron-carbon alloys such as steels, which contain between 0.003 and about 2% carbon, the majority lying in the range of 0.01 to 1.2%, and cast irons with 2 to 4% carbon. At the carbon contents typical of steels, iron carbide, Fe3C, also known as smantite, is formed. This leads to the formation of pearlite, which in a microscope can be seen to consist of alternate lathes of alpha ferrite and smantite. Smantite is harder and stronger than ferrite but is much less malleable, so that vastly differing mechanical properties are obtained by varying the amount of carbon. At the higher carbon contents typical of cast irons, carbon may separate out as either smantite or graphite, depending on the manufacturing conditions. Again, a wide range of properties is obtained. This versatility of iron-carbon alloys leads to their widespread use in engineering and explains why iron is by far the most important of all the industrial metals. History. There is evidence that meteorites were used as a source of iron before 3000 BC, but extraction of the metal from ores dates from about 2000 BC. Production seems to have started in the copper-producing regions of Anatolia and Persia, where the use of iron compounds as fluxes to assist in melting may have accidentally caused metallic iron to accumulate on the bottoms of copper smelting furnaces. When iron making was properly established, two types of furnace came into use. Bowl furnaces were constructed by digging a small hole in the ground and arranging for air from a bellows to be introduced through a pipe or two-ear. Stone-built shaft furnaces, on the other hand, relied on natural draft, although they too sometimes used tuers. In both cases, smelting involved creating a bed of red-hot charcoal to which iron ore mixed with more charcoal was added. Chemical reduction of the ore then occurred, but, since primitive furnaces were incapable of reaching temperatures higher than 1150 degrees Celsius, 2100 degrees Fahrenheit, the normal product was a solid lump of metal known as a bloom. This may have weighed up to 5 kilograms, 11 pounds, and consisted of almost pure iron with some entrapped slag and pieces of charcoal. The manufacture of iron artifacts then required a shaping operation, which involved heating blooms in a fire and hammering the red-hot metal to produce the desired objects. Iron made in this way is known as wrought iron. Sometimes too much charcoal seems to have been used, and iron-carbon alloys, which have lower melting points and can be cast into simple shapes, were made unintentionally. The applications of this cast iron were limited because of its brittleness, and in the early Iron Age only the Chinese seem to have exploited it. Elsewhere, wrought iron was the preferred material. Although the Romans built furnaces with a pit into which slag could be run off, little change in iron-making methods occurred until medieval times. By the 15th century, many bloomeries used low-shaft furnaces with water power to drive the bellows, and the bloom, which might weigh over 100 kilograms, was extracted through the top of the shaft. The final version of this kind of bloomery hearth was the Catalan forge, which survived in Spain until the 19th century. Another design, the high bloomery furnace, had a taller shaft and evolved into the 3-meter, 10-foot, high stuccofen, which produced blooms so large they had to be removed through a front opening in the furnace. In 1879, Sidney Gilchrist Thomas and Percy Gilchrist adapted the Bessemer converter for use with phosphoric pig iron. As a result, the basic Bessemer, or Thomas, process was widely adopted on the continent of Europe, where high phosphorus iron ores were abundant. For about 100 years, the open hearth and Bessemer-based processes were jointly responsible for most of the steel that was made, before they were replaced by the basic oxygen and electric arc furnaces. Apart from the injection of part of the fuel through tuas, the blast furnace has employed the same operating principles since the early 19th century. Furnace size has increased markedly, however, and one large modern furnace can supply a steelmaking plant with up to 10,000 tons of liquid iron per day. Throughout the 20th century, many new iron-making processes were proposed, but it was not until the 1950s that potential substitutes for the blast furnace emerged. Direct reduction, in which iron ores are reduced at temperatures below the metal's melting point, had its origin in such experiments as the Wiberg-Sodaffors process introduced in Sweden in 1952 and the Hill process introduced in Mexico in 1957. Few of these techniques survived, and those that did were extensively modified. Another alternative iron-making method, smelting reduction, had its forerunners in the electric furnaces used to make liquid iron in Sweden and Norway in the 1920s. The technique grew to include methods based on oxygen steelmaking converters using coal as a source of additional energy, and in the 1980s it became the focus of extensive research and development activity in Europe, Japan, and the United States.